Welcome to our deep dive into the fascinating world of bucket wheel excavators, often abbreviated as BWEs. In this chapter, we will introduce you to what bucket wheel excavators are, their history, their primary components, and why they are crucial in modern mining and large-scale earth-moving operations. By the end of this chapter, you will have a strong foundational understanding of these colossal machines and their significance in the mining industry, especially in the United States and around the world. A bucket wheel excavator is one of the largest land vehicles ever constructed. It is an extraordinary example of human engineering, combining immense power, precision, and efficiency to perform the enormous task of removing overburden in mining operations. Overburden refers to the soil, rock, or other materials that lie above a mineral deposit, such as coal, lignite, or other valuable resources. BWEs are essential for surface mining operations, where removing large quantities of overburden quickly is a critical part of ensuring that mining projects remain profitable and sustainable. The origins of bucket wheel excavators date back to the early 20th century. The concept of using rotating buckets to excavate materials can be traced to Europe, particularly Germany, which became a hub for heavy mining machinery innovation. Over the decades, these machines evolved from relatively small and simple designs to massive, fully automated systems capable of moving thousands of cubic meters of material every day. Today, some of the largest BWEs in operation are in lignite mines in Germany and other parts of Europe, but similar technology is increasingly used in North America, including the United States, to enhance efficiency in mining operations. A bucket wheel excavator is primarily composed of several key components. The most recognizable feature is, of course, the massive rotating bucket wheel itself. These buckets are attached to a large circular wheel, which continuously scoops up material as the wheel rotates. Each bucket is designed to dig into the ground with high precision and carry a fixed amount of material to the next stage of the process. Attached to the bucket wheel is the boom, a long, rigid structure that supports the wheel and allows it to reach deep into the mining face. The boom is connected to a rotating superstructure that enables the entire excavator to pivot, giving it the ability to cover a wide area without needing to move the entire machine frequently. The superstructure itself rests on a series of tracks or crawlers, which allow the enormous machine, sometimes weighing thousands of tons, to move across the mining site. In addition to these mechanical components, modern BWEs are equipped with advanced control systems. Operators can control the speed of the bucket wheel, the movement of the boom, and the direction of the machine with precision. Many modern machines even include semi-automated or fully automated functions, reducing the risk to human operators and increasing productivity. Sensors and monitoring systems track every aspect of the machine's performance, from the amount of material being moved to the mechanical health of critical components. The sheer scale of a bucket wheel excavator is awe-inspiring. Some of the largest models are over 700 feet long, over 300 feet tall, and weigh thousands of tons. These machines are capable of moving over 100,000 cubic meters of material per day, which is equivalent to hundreds of fully loaded dump trucks. Their efficiency allows mining operations to proceed at an astonishing pace, dramatically reducing the time needed to access valuable mineral deposits. In terms of their impact, BWEs are not just machines, they are game changers for the mining industry. In the United States, where coal and other mineral extraction remains an important industry, these machines help mining companies remain competitive. By using BWEs, companies can reduce labor costs, improve safety, and increase output, all while minimizing environmental disruption compared to smaller, less efficient equipment. Finally, it's important to understand that operating a bucket wheel excavator requires a highly skilled team. Engineers, operators, and maintenance personnel must work in coordination to ensure the machine runs smoothly. Regular inspections and preventive maintenance are critical because any mechanical failure can lead to costly downtime. The combination of advanced engineering, precise operation, and careful maintenance makes BWEs a marvel of modern industrial technology. In summary, Chapter 1 has provided an overview of what bucket wheel excavators are, their history, key components, and their significance in modern mining. We've explored how these machines evolved into the massive, efficient systems used today, and why they are particularly important in countries like the United States. In the next chapter, we will delve deeper into the mechanics of bucket wheel excavators, exploring how the bucket wheel works, how material is transported, and how these machines achieve such incredible efficiency. Welcome to Chapter 2 of our series on bucket wheel excavators. In this chapter, we will explore the intricate mechanics behind these massive machines, explaining exactly how they operate, how materials are transported, and why they are able to perform the monumental task of moving thousands of cubic meters of earth every single day. Understanding the mechanics is key for anyone interested in mining technology, heavy machinery, or industrial engineering, especially for applications in the United States. At the heart of every bucket wheel excavator is the bucket wheel itself. This massive wheel is equipped with a series of buckets arranged along its circumference. Each bucket is specially designed to dig into soil, clay, rock, or other materials, scoop them up, and carry them along the wheel's rotation. The bucket design is critical. It must be strong enough to handle abrasive materials, shaped to reduce spillage, and balanced to maintain smooth rotation. Depending on the machine, a bucket may hold anywhere from 1 to 15 cubic meters of material, and with dozens of buckets on a single wheel, the total volume moved per rotation is enormous. The rotation of the bucket wheel is powered by powerful electric motors or hydraulic systems, often controlled with precision by computer systems. The speed of rotation is carefully managed. Too fast, and the buckets may spill their load or cause undue stress on the machinery. Too slow, and the efficiency of material removal drops significantly. Engineers must calculate the optimal rotation speed based on the type of material being excavated and the depth of the mining face. Once the buckets scoop up material, it is immediately deposited onto a conveyor system attached to the excavator. This system is a marvel of engineering in itself. The conveyor consists of a series of belts that transport material from the bucket wheel to the stacking area or directly to trucks or other transport systems. The angle, speed, and length of the conveyor belts are all carefully designed to minimize spillage and ensure a continuous flow of material. In some cases, these conveyors can extend for several hundred feet, allowing the excavator to work in a wide area without needing to move frequently. The boom, which supports the bucket wheel, is another crucial component. The boom is a long, rigid arm that can be adjusted in height and angle to reach different parts of the mining face. Hydraulic cylinders and mechanical winches allow operators to raise, lower, or extend the boom, giving the excavator incredible flexibility. The ability to adjust the boom means that the excavator can remove overburden efficiently while avoiding obstacles, uneven terrain, or sensitive environmental areas. Equally impressive is the crawler or track system that allows these massive machines to move across the mining site. A fully loaded bucket wheel excavator can weigh thousands of tons, yet its tracks are designed to distribute this immense weight evenly to prevent sinking or damage to the ground. Movement is slow and deliberate, often only a few meters per hour, but the tracks allow the machine to cover the mining area without needing to disassemble or rebuild components. Modern BWEs also feature automated guidance systems to maintain precise positioning while moving or digging. Another critical aspect of operation is automation and control systems. Modern bucket wheel excavators use a combination of human operators and automated systems to ensure maximum efficiency. Operators monitor the machine's performance, control the movement of the boom and bucket wheel, and adjust conveyor speeds as needed. Meanwhile, sensors continuously track material load, wear on components, and energy consumption. These systems can detect problems before they become serious, alerting operators to perform maintenance or adjust operation. Some of the latest BWEs even have fully automated functions, allowing the machine to dig, transport, and deposit material with minimal human intervention. The mechanical coordination of all these components is astonishing. The bucket wheel, boom, conveyors, tracks, and control systems all work in harmony. For instance, as the bucket wheel scoops material, the conveyor must immediately begin transporting it away. At the same time, the boom may be adjusting its angle, while the tracks slowly reposition the excavator. This requires precise engineering, careful planning, and expert operation. Energy efficiency is another important consideration. Running such enormous machinery requires immense amounts of power, often in the form of electricity or diesel engines. Engineers design BWEs to minimize energy waste while maximizing output. This includes optimizing the rotation of the bucket wheel, the speed of conveyors, and the movement of the tracks. By improving efficiency, mining companies can save significant costs and reduce their environmental footprint. Maintenance and safety are also integral to the operation of bucket wheel excavators. Daily inspections are conducted to check the condition of the buckets, hydraulic systems, conveyor belts, and structural components. Preventive maintenance helps avoid breakdowns, which could halt operations and incur high costs. Safety protocols are strictly followed, especially considering the enormous scale and power of these machines. Operators are trained to handle emergencies, monitor load limits, and respond to mechanical issues quickly. Finally, the operation of bucket wheel excavators demonstrates a fascinating intersection of mechanical engineering, automation, and mining science. It's not just about digging and moving material, it's about precision, efficiency, and maximizing productivity while ensuring safety. These machines represent some of the most advanced terrestrial engineering feats ever created, and understanding their mechanics gives us insight into the incredible capabilities of modern industrial machinery. In summary, Chapter 2 has explored the detailed mechanics of bucket wheel excavators, including the functioning of the bucket wheel, the role of the boom and conveyor systems, the importance of tracks for mobility, and the integration of automation and control systems. We have seen how these machines coordinate complex operations to achieve extraordinary efficiency, and why expert operation and maintenance are critical to their success. In the next chapter, we will take a closer look at the types of bucket wheel excavators, their variations, and the specific mining applications where each type excels, helping us understand how these incredible machines are adapted to different environments and materials around the world, including the United States. Welcome to Chapter 3 of our comprehensive series on bucket wheel excavators. In this chapter, we will explore the different types of bucket wheel excavators, their specific applications, and how mining engineers choose the right machine for a particular job. Understanding these variations is essential for anyone interested in mining operations, industrial engineering, or large-scale earth-moving projects, particularly in the United States where efficiency and productivity are critical to mining success. Bucket wheel excavators come in several sizes and configurations, each tailored to specific mining conditions and material types. Broadly, we can categorize BWEs based on their size, mobility, and application. Some are smaller and more mobile, designed for flexible use in medium-scale operations, while others are enormous machines built to handle continuous large-scale extraction in lignite or coal mines. One of the most common types is the fixed or stationary bucket wheel excavator. These machines are typically anchored to a single location within a mine and operate in a specific area for an extended period. The advantage of stationary BWEs is their ability to handle extremely high volumes of material without moving frequently. They are ideal for large, uniform deposits, where the overburden is relatively consistent and the need for mobility is minimal. Their conveyors are often extended to transport material over long distances, feeding nearby processing facilities or stockpiles. In contrast, mobile bucket wheel excavators are mounted on tracks or crawlers, allowing them to move across the mining site. This type is especially useful in open-pit mining operations where the mining face changes frequently, or where the excavator needs to follow a seam of material across a large area. Mobility adds versatility but also requires careful engineering to ensure stability and efficiency while moving, particularly on uneven terrain. Mobile BWEs are highly valued in the United States for operations where coal, lignite, or other minerals are extracted from large surface mines with variable topography. Another important classification is based on the capacity of the bucket wheel. Small to medium BWEs have smaller bucket wheels and are suited for less abrasive materials or mines with moderate production targets. Large BWEs, however, have massive wheels with dozens of large buckets, capable of moving over 100,000 cubic meters of material per day. These massive machines are engineered for continuous, high-volume operations and are most often found in coal or lignite mines in Europe, Asia, and increasingly in the United States. The material being excavated also influences the choice of bucket wheel excavator. For example, soft materials such as soil, clay, or lignite can be excavated efficiently with relatively standard bucket designs. However, when mining harder materials such as sandstone, iron ore, or heavily compacted overburden, engineers select machines with reinforced buckets, stronger structural components, and more powerful motors to handle the additional resistance. Each type of material presents unique challenges in terms of wear, energy consumption, and excavation efficiency, so matching the right BWE to the right application is critical. In addition to size and material considerations, bucket wheel excavators are also classified by their conveyor and stacking capabilities. Some BWEs feature simple conveyors that deposit material nearby, while others include integrated stacking systems, allowing them to create large stockpiles in a single operation. Advanced machines may also include integrated sorting and screening systems, separating materials as they are excavated to improve processing efficiency. These capabilities are increasingly important in modern mining operations, especially in the United States, where regulatory and environmental considerations require careful handling of mine materials. Mining applications for BWEs vary widely. In coal and lignite mining, these machines are indispensable, allowing operators to remove overburden quickly and expose the mineral seam beneath. In industrial mineral extraction, such as phosphate, clay, or salt mining, smaller BWEs provide precise excavation without damaging surrounding resources. In large-scale earth-moving projects, BWEs can be used for canal construction, land reclamation, and other infrastructure projects that require massive material movement over extended areas. Safety and efficiency also play a significant role in selecting the appropriate BWE for a specific application. In environments with high dust, vibration, or irregular terrain, machines with robust structures, advanced dust control, and real-time monitoring systems are preferred. Some BWEs are equipped with operator cabins elevated above the mining face, providing better visibility and reducing exposure to dust and noise. Automation features, including remote monitoring and semi-automatic operation, further enhance safety while maintaining high productivity. Another important application is in environmental mining and reclamation projects. Some modern BWEs are designed not only to excavate efficiently, but also to minimize environmental impact. They can be used to remove overburden carefully, allowing for controlled restoration of land after mining operations. In the United States, environmental regulations often require mining companies to rehabilitate land post-mining, and bucket wheel excavators provide an effective way to accomplish this while maintaining operational efficiency. Finally, it's worth noting that engineers often customize BWEs for specific project requirements. Factors such as depth of excavation, type of material, project timeline, and terrain all influence the final design. As a result, no two BWEs are exactly alike. Each machine represents a combination of engineering innovation, practical application, and adaptation to the unique conditions of the mining site. In summary, Chapter 3 has explored the different types of bucket wheel excavators, including fixed, mobile, small, and large capacity machines. We've examined how engineers select the right machine based on material, terrain, capacity, and environmental requirements. Additionally, we've discussed the wide range of applications, from coal mining to industrial mineral extraction, infrastructure projects, and land reclamation. Understanding these variations gives us a clearer picture of why bucket wheel excavators are such a vital part of modern mining operations, including in the United States. In the next chapter, we will delve into the maintenance, safety, and operational challenges of bucket wheel excavators, helping us understand the complexities of keeping these enormous machines running efficiently and safely over many years of demanding work. Welcome to Chapter 4 of our comprehensive series on bucket wheel excavators. In this chapter, we will explore one of the most critical aspects of operating these enormous machines: maintenance, safety, and the operational challenges that engineers and operators face every day. Understanding these elements is essential for anyone involved in mining operations or industrial machinery management, especially in the United States, where regulatory compliance, efficiency, and worker safety are top priorities. Operating a bucket wheel excavator is not just about digging and moving material. These machines are incredibly complex, with thousands of moving parts, massive loads, and intricate control systems. Without proper maintenance, even the smallest mechanical issue can escalate into a major problem, leading to costly downtime or potential accidents. Maintenance of BWEs is a continuous process, involving daily inspections, preventive care, and periodic overhauls. Daily inspections are the first line of defense. Operators and maintenance personnel check critical components, such as the bucket wheel, boom, hydraulic systems, conveyor belts, and track assemblies. Any signs of wear, cracks, or misalignment are immediately addressed. The bucket wheel, for example, endures extreme stress as it scoops up tons of material, so engineers frequently check for worn edges, loose bolts, and signs of fatigue in the metal. Conveyor systems also require constant monitoring to prevent jams, misalignment, or belt slippage, which could disrupt the flow of material and affect overall efficiency. Preventive maintenance is another essential aspect of keeping BWEs operational. This includes lubricating moving parts, replacing worn components, tightening fasteners, and checking hydraulic fluid levels. Preventive maintenance reduces the likelihood of sudden failures and extends the lifespan of the machine. For large machines that operate continuously, preventive maintenance schedules are meticulously planned to minimize downtime and ensure that the excavator remains productive. A significant operational challenge is the enormous wear and tear these machines experience. Bucket wheel excavators often operate in harsh environments, encountering abrasive soils, rocks, and other materials that can quickly erode metal surfaces. Engineers use specialized materials, such as high-strength steel and wear-resistant coatings, to combat these effects. Regular replacement of worn parts, particularly the buckets, teeth, and cutting edges, is necessary to maintain optimal performance. Safety is paramount when operating such massive machinery. A fully loaded BWE can weigh thousands of tons, and a malfunction could have catastrophic consequences. Operator training is rigorous, focusing on both routine operation and emergency procedures. Safety protocols include maintaining safe distances from moving parts, monitoring structural stresses, and adhering to strict operational limits. Elevated operator cabins and protective barriers provide additional safety, reducing exposure to dust, noise, and mechanical hazards. Another operational challenge is environmental conditions. BWEs often work in extreme heat, cold, or wet conditions, which can affect both machinery and personnel. For instance, extreme temperatures may cause hydraulic fluids to thicken or thin, affecting performance, while rain or mud can reduce traction on tracks and complicate excavation. Engineers and operators must constantly adjust machine settings and operation techniques to compensate for these environmental factors. The integration of automation and monitoring systems has significantly improved safety and operational efficiency. Sensors constantly monitor parameters such as vibration, load, temperature, and hydraulic pressure. Advanced control systems can detect potential failures before they occur, alert operators, and in some cases, take corrective action automatically. This predictive maintenance capability is a game changer, reducing unplanned downtime and increasing overall safety. Despite these technological advancements, challenges still remain. Coordinating the movement of the bucket wheel, boom, conveyors, and tracks requires precise planning and communication among the operating team. Any misalignment or timing error can lead to inefficiencies or even damage. Large BWEs also have limited mobility, meaning repositioning them across a mining site requires careful planning, sometimes involving days of preparation and specialized support equipment. Energy consumption is another operational consideration. BWEs are highly energy-intensive, often consuming hundreds of kilowatts of power continuously. Engineers must balance operational speed, efficiency, and energy use to ensure that mining operations remain cost-effective. Energy-efficient design, optimized load distribution, and careful monitoring help mitigate these challenges. Maintenance and safety challenges also extend to long-term structural health. Regular inspections using modern techniques, such as ultrasonic testing, laser scanning, and thermal imaging, help identify stress points, cracks, or other weaknesses before they lead to catastrophic failures. Engineers create detailed maintenance logs and predictive schedules to keep every component functioning optimally. Finally, human factors play a crucial role in operational safety. Even with advanced automation, skilled operators are essential to interpret sensor data, respond to unexpected conditions, and make critical decisions. Ongoing training, adherence to standard operating procedures, and a strong safety culture are vital to the successful operation of BWEs. In summary, Chapter 4 has highlighted the complex maintenance, safety, and operational challenges associated with bucket wheel excavators. We've explored daily inspections, preventive maintenance, wear and tear management, environmental factors, automation, energy efficiency, long-term structural health, and the critical role of human operators. Understanding these challenges is essential for maintaining efficiency, safety, and productivity, especially in large-scale mining operations in the United States. In the next chapter, we will examine the environmental impact and sustainability considerations of bucket wheel excavators, exploring how these machines affect ecosystems, how mining companies mitigate these effects, and the future of environmentally responsible excavation. Welcome to Chapter 5 of our series on bucket wheel excavators. In this chapter, we will explore one of the most important aspects of modern mining: the environmental impact of bucket wheel excavators and the sustainability measures that mining companies implement to reduce these effects. Understanding the relationship between these massive machines and the environment is critical, particularly in the United States, where environmental regulations are stringent and public awareness of sustainable practices is high. Bucket wheel excavators are marvels of engineering, capable of moving thousands of cubic meters of material every day. However, their size and power also mean that they have significant environmental footprints. The primary environmental impact comes from the sheer scale of land disturbance. Surface mining, which is where BWEs are primarily used, requires the removal of overburden, soil, rocks, and other materials that cover mineral deposits. This process dramatically alters the landscape, affecting local ecosystems, wildlife habitats, and soil composition. Another important consideration is dust and air pollution. As the bucket wheel scoops and transports material, fine particles are released into the air. In coal or lignite mining operations, this can include coal dust or other particulate matter, which can impact air quality and pose health risks to workers and nearby communities. Mining companies in the United States are required to implement dust suppression measures, such as water sprays, dust collectors, and enclosure systems for conveyors and processing areas, to minimize airborne particles. Noise pollution is another significant effect of bucket wheel excavators. These machines generate constant noise from the rotation of the bucket wheel, movement of the boom, operation of conveyors, and power systems. Noise can disrupt wildlife, affect nearby residents, and contribute to hearing risks for workers. Modern BWEs are designed with noise reduction technologies, including quieter motors, insulated cabins, and noise barriers, to address these concerns. Energy consumption is also a critical environmental consideration. Bucket wheel excavators are highly energy-intensive machines, often consuming hundreds of kilowatts continuously. In large mining operations, this translates to substantial electricity use, which, depending on the energy source, can contribute to carbon emissions. To improve sustainability, many mining companies are exploring energy-efficient designs, optimized operations, and renewable energy integration, including solar and wind power, to reduce the carbon footprint of their excavators. Water management is another environmental challenge. Surface mining operations often encounter groundwater or require water for dust suppression. Improper water handling can lead to soil erosion, contamination, and disruption of local water supplies. Mining companies address these issues by implementing controlled drainage systems, water recycling processes, and careful monitoring of water quality to prevent negative impacts on the surrounding environment. Rehabilitation and land reclamation are central to sustainable mining practices involving bucket wheel excavators. After an area has been mined, it is essential to restore the land to a safe, stable, and usable condition. This includes replacing topsoil, regrading the landscape, planting vegetation, and creating habitats for wildlife. In the United States, reclamation is often a legal requirement, and BWEs play a role in these processes as well, by carefully relocating soil and materials to support environmental restoration efforts. Another sustainability consideration is the reuse and recycling of materials. Some modern BWEs are designed to sort excavated materials, separating valuable minerals from waste. This reduces the amount of material sent to disposal sites and allows for more efficient use of resources. Additionally, components of BWEs themselves, such as metal parts and hydraulic systems, are designed to be maintained, refurbished, or recycled at the end of their operational life, minimizing waste and environmental impact. Mining companies also consider the impact on local communities. Large-scale excavation can disrupt transportation, create noise and dust, and alter the local landscape. Responsible operators work closely with local governments and communities to mitigate these effects, provide compensation when necessary, and ensure that mining operations align with environmental and social regulations. Public transparency and community engagement are key aspects of sustainable operations. In recent years, technology has played a major role in improving the sustainability of bucket wheel excavators. Sensors and automation systems allow operators to optimize excavation paths, reduce unnecessary movement, and monitor environmental conditions in real time. Advanced predictive analytics can help schedule maintenance efficiently, reducing energy consumption and preventing accidents that could harm the environment. By integrating technology, mining operations can achieve higher productivity while minimizing ecological disruption. Finally, it's important to recognize that the future of sustainable mining depends on continuous innovation. Research and development in the fields of energy efficiency, low-emission power systems, advanced material handling, and environmentally friendly excavation practices are shaping the next generation of bucket wheel excavators. In the United States, these innovations are increasingly aligned with federal and state regulations aimed at protecting ecosystems, conserving resources, and promoting responsible industrial practices. In summary, Chapter 5 has explored the environmental impact and sustainability considerations of bucket wheel excavators. We've examined land disturbance, dust and noise pollution, energy and water use, land reclamation, recycling, community engagement, and the role of technology in promoting sustainable practices. Understanding these factors is crucial for anyone involved in mining or industrial operations, and highlights the balance between industrial efficiency and environmental responsibility. In the next chapter, we will focus on the future of bucket wheel excavators, including technological advancements, automation, and potential innovations that will shape the next generation of these incredible machines. Welcome to Chapter 6 of our series on bucket wheel excavators. In this chapter, we will explore the future of these massive machines, focusing on technological advancements, automation, and innovations that are set to redefine the mining industry. Understanding the direction in which this technology is heading is essential for engineers, mining operators, and anyone interested in industrial machinery, especially in the United States where efficiency, sustainability, and safety are driving forces in mining operations. Bucket wheel excavators have already achieved remarkable engineering feats, but the future promises even greater developments. One of the most significant trends is automation and artificial intelligence. Modern BWEs are increasingly equipped with semi-automated systems, but the next generation is expected to feature full autonomy. This means machines will be able to navigate, excavate, and transport materials with minimal human intervention, using advanced AI algorithms to optimize every movement and ensure maximum efficiency. Autonomous operation reduces human error, improves safety, and allows machines to operate continuously without fatigue. Sensor technology is another area of rapid advancement. Future BWEs will feature an array of sensors capable of monitoring structural integrity, material load, environmental conditions, and machine performance in real time. These sensors will provide predictive analytics, alerting operators or automated systems to potential issues before they cause downtime. For example, sensors can detect wear on bucket edges, misalignment in conveyor belts, or excessive vibration, allowing for preemptive maintenance that keeps operations smooth and uninterrupted. Energy efficiency will also see significant improvements. Next-generation BWEs are likely to integrate hybrid power systems, combining electricity, batteries, and renewable energy sources to reduce carbon emissions and operational costs. Energy recovery systems may capture and reuse energy generated during excavation or braking operations. This focus on sustainability aligns with global efforts to reduce the environmental impact of mining while maintaining high productivity. Material handling and processing will also become more advanced. Future BWEs are expected to include integrated sorting, screening, and even processing systems directly on the excavator. This means that raw material can be partially processed or sorted immediately after excavation, reducing the need for secondary handling, transportation, and energy consumption. This not only improves efficiency but also supports environmental sustainability by reducing waste and minimizing resource use. Another exciting development is the use of digital twins, virtual models of the excavator that simulate operation in real time. Engineers can use these digital twins to optimize excavation strategies, predict maintenance needs, and train operators without risking damage to the actual machine. This approach allows for precise planning and experimentation, improving both performance and safety in real-world operations. Connectivity and remote operation will become increasingly important. Future BWEs may be fully integrated into centralized mining control centers, where operators can monitor and control multiple machines from a single location. High-speed communication networks and real-time data analysis will allow operators to coordinate excavation, transportation, and material processing seamlessly across an entire mining site. This level of connectivity enhances productivity, safety, and decision-making efficiency. Advanced materials and construction techniques will further enhance the durability and efficiency of BWEs. Engineers are exploring lightweight yet strong materials, wear-resistant coatings, and modular components that can be easily replaced or upgraded. These innovations will extend the lifespan of machines, reduce maintenance requirements, and allow for faster adaptation to changing mining conditions or project requirements. Environmental innovation will continue to shape the design of future BWEs. Machines will be designed to minimize soil disruption, reduce dust and noise pollution, and manage water and energy resources more effectively. Automation will also contribute to more precise excavation, reducing the environmental footprint of mining activities and supporting sustainable development goals. Finally, the human role in future bucket wheel excavators will evolve. While automation will handle many operational tasks, skilled engineers and operators will remain essential for overseeing operations, interpreting data, making critical decisions, and ensuring that machines operate safely and efficiently. Continuous training and collaboration between humans and machines will define the next era of mining excellence. In summary, Chapter 6 has explored the future advancements and technological innovations in bucket wheel excavators. We've discussed automation and AI, advanced sensors, energy efficiency, integrated material processing, digital twins, remote operation, advanced materials, environmental innovations, and the evolving role of human operators. The future of BWEs promises safer, more efficient, and more sustainable mining operations, particularly in the United States and other regions where cutting-edge technology drives industrial progress. In the next chapter, we will focus on global case studies and notable examples of bucket wheel excavators, highlighting some of the largest, most productive, and most innovative machines in operation around the world. Welcome to Chapter 7 of our comprehensive series on bucket wheel excavators. In this chapter, we will explore global case studies and highlight some of the most notable examples of these engineering marvels. Understanding real-world applications allows us to appreciate the scale, efficiency, and impact of bucket wheel excavators in mining operations across the globe, including their relevance in the United States. One of the most famous examples of a bucket wheel excavator is the Bagger 288, built by the German company Krupp for mining operations in the Hambach lignite mine. Bagger 288 holds the record as one of the largest land vehicles ever constructed. Measuring over 700 feet in length and standing nearly 315 feet tall, it can move up to 240,000 cubic meters of earth per day. This incredible capacity demonstrates the extraordinary efficiency of modern BWEs, capable of replacing hundreds of dump trucks and hundreds of workers with a single machine. The Bagger 288 has become an iconic symbol of large-scale mining engineering, inspiring engineers worldwide to develop even more efficient and innovative machines. Another notable example is the Bagger 293, also from Germany, which currently holds the title of the heaviest terrestrial vehicle ever built. It weighs over 14,000 tons and is used in the Garzweiler coal mine. The Bagger 293 is designed for continuous, high-volume operations and features advanced automation and monitoring systems. Its bucket wheel has a diameter of over 70 feet and contains 18 buckets, each capable of holding several cubic meters of material. Machines like the Bagger 293 illustrate the peak of mechanical engineering and operational efficiency, showing what is possible when size, power, and precision come together. In Asia, particularly in India, large bucket wheel excavators have been deployed for coal and lignite mining to meet the growing energy demands of the region. These machines are often adapted to local mining conditions, such as softer or more abrasive soil, and are integrated with advanced conveyor systems to transport materials efficiently. Their application demonstrates the global versatility of BWEs and their ability to operate in diverse environmental and operational conditions. In North America, particularly the United States, bucket wheel excavators are widely used in lignite and coal surface mining operations. While the machines may not always reach the colossal scale of the German BWEs, they are engineered for efficiency, safety, and environmental compliance. US-based BWEs are often equipped with advanced monitoring systems, automation, and dust control technologies, reflecting the country's regulatory standards and emphasis on operational safety. Large mines in Texas, North Dakota, and Wyoming utilize these machines to maximize productivity while adhering to strict environmental regulations. Some smaller but highly specialized BWEs are used in industrial mineral mining worldwide. These machines may be less massive, but are designed for precision and adaptability. For example, in phosphate, clay, and salt mines, BWEs provide consistent, controlled excavation, ensuring that the surrounding environment is minimally impacted while still achieving high productivity. Their success in these applications highlights the adaptability of bucket wheel technology to different mining scenarios and materials. Another interesting case study comes from land reclamation and large-scale civil engineering projects. In some parts of Europe and Asia, BWEs have been used to reshape landscapes for construction projects, canals, and artificial lakes. These applications demonstrate that the capabilities of bucket wheel excavators extend beyond traditional mining. Their ability to move massive volumes of earth quickly and efficiently makes them ideal for projects where precision and scale are equally important. It's also worth noting that some BWEs are temporary installations, built for specific projects or mine expansions. These machines are later dismantled, refurbished, or relocated to new sites. This approach maximizes their economic and operational value, as well as demonstrates the modular and adaptable nature of modern BWE engineering. Global case studies also highlight the importance of maintenance, safety, and operational planning. Machines like Bagger 288 and Bagger 293 require highly skilled teams for operation and upkeep, including engineers, operators, and maintenance personnel. These examples illustrate that no matter how technologically advanced the machines become, human expertise remains a critical component of successful mining operations. Finally, the global perspective emphasizes the evolution of bucket wheel technology. From the earliest European designs to the massive modern machines in Germany, India, and the United States, BWEs have continuously adapted to meet increasing demands for efficiency, environmental compliance, and safety. Each case study provides valuable lessons in engineering innovation, operational strategy, and sustainability, helping mining companies worldwide optimize their excavators for specific needs. In summary, Chapter 7 has provided a global overview of notable bucket wheel excavators, including iconic machines like Bagger 288 and Bagger 293, as well as examples from North America, Asia, and specialized industrial applications. We've seen how these machines vary in size, design, and functionality, and how global case studies illustrate best practices in efficiency, safety, and environmental sustainability. Understanding these real-world examples gives us a practical appreciation of the engineering marvels that bucket wheel excavators represent and their critical role in modern mining operations. In the next chapter, we will focus on economic and industrial significance, exploring how BWEs contribute to productivity, cost efficiency, and the overall mining industry's impact on the global economy, with a particular emphasis on the United States. Welcome to Chapter 8 of our series on bucket wheel excavators. In this chapter, we will explore the economic and industrial significance of these enormous machines, discussing how they impact productivity, cost efficiency, and the mining industry as a whole. Understanding the economic implications of BWEs is crucial, particularly in the United States, where mining plays a vital role in energy production, industrial supply chains, and regional economies. Bucket wheel excavators are not just impressive engineering marvels, they are key drivers of productivity in large-scale mining operations. A single BWE can move tens of thousands of cubic meters of material per day, which would otherwise require hundreds of trucks and hundreds of workers. This extraordinary efficiency reduces labor costs, minimizes fuel consumption for multiple vehicles, and allows mining companies to achieve output levels that would be impossible with conventional equipment. The cost efficiency of BWEs is one of their most significant economic benefits. While the initial investment in a bucket wheel excavator can be substantial, often in the tens of millions of dollars, the long-term return on investment is remarkable. These machines operate continuously, 24 hours a day, 7 days a week, significantly reducing per-unit excavation costs. In large-scale coal or lignite mines, the cost savings achieved by using a single BWE compared to traditional trucks and shovels can be enormous, making these machines indispensable in industrial mining. BWEs also contribute to job creation and industrial growth. While automation reduces the need for certain manual tasks, BWEs require highly skilled engineers, operators, and maintenance personnel. Training programs and specialized careers in mining technology, mechanical engineering, and industrial operations are directly supported by the use of such advanced machinery. In the United States, this translates to well-paying jobs, educational opportunities, and the development of expertise in heavy machinery operation and maintenance. The impact on regional economies is also notable. Mining operations that utilize BWEs often support local infrastructure, transportation networks, and auxiliary services. Towns and regions near large surface mines benefit from increased economic activity, ranging from housing and retail to service industries. By increasing efficiency and productivity, BWEs enable mining companies to maintain operations at scale, thereby supporting local and national economies. From an industrial perspective, BWEs are crucial in maintaining consistent supply chains for raw materials. Coal, lignite, and other minerals extracted using BWEs are essential for energy production, steel manufacturing, cement production, and other critical industries. Reliable and efficient excavation ensures that these industries have a steady supply of raw materials, reducing the risk of production delays or shortages. In the United States, where energy security and industrial competitiveness are strategic priorities, BWEs play a vital role in meeting national demand. The use of BWEs also supports sustainable economic practices. By moving large volumes of material efficiently, companies can reduce fuel consumption, lower emissions from auxiliary vehicles, and optimize material transport systems. This not only reduces operational costs, but also aligns with growing environmental and sustainability requirements. Economically, sustainable practices help mining companies avoid fines, regulatory delays, and reputational damage, which can be costly over time. Another economic advantage is the flexibility and scalability of BWEs. These machines can be adapted to different mining sites, material types, and production targets. Companies can invest in machines tailored to their specific needs, whether it's a massive lignite mine in North Dakota or a medium-scale industrial mineral operation. This adaptability ensures that BWEs remain economically viable across a wide range of applications and market conditions. Global competition also highlights the economic importance of bucket wheel excavators. Countries and companies that invest in advanced BWEs gain a competitive advantage in resource extraction. By maximizing efficiency, reducing downtime, and maintaining consistent output, mining operations in the United States and around the world can remain profitable and competitive in the global market. Finally, BWEs contribute to the long-term strategic planning of the mining industry. By providing predictable, high-volume excavation capabilities, these machines allow companies to plan production schedules, manage supply chains, and allocate resources effectively. This strategic value is especially important in industries where market demand fluctuates, energy prices change, or new regulations are implemented. A reliable BWE operation provides the foundation for long-term industrial and economic stability. In summary, Chapter 8 has explored the economic and industrial significance of bucket wheel excavators. We've discussed their role in productivity, cost efficiency, job creation, regional economic impact, supply chain reliability, sustainability, flexibility, global competitiveness, and strategic planning. Understanding these economic implications highlights why BWEs are not only engineering marvels but also critical assets for the mining industry, particularly in the United States, where their impact resonates across energy, industrial production, and regional development. In the next chapter, we will focus on challenges and limitations, exploring what factors restrict the use of bucket wheel excavators, including operational, environmental, and economic constraints, and how the industry is addressing these challenges. Welcome to Chapter 9 of our series on bucket wheel excavators. In this chapter, we will explore the challenges and limitations of these massive machines. While bucket wheel excavators are engineering marvels capable of moving enormous amounts of material efficiently, they are not without constraints. Understanding these challenges is essential for operators, engineers, and industrial planners, especially in the United States, where mining projects are subject to complex environmental, economic, and operational considerations. One of the primary challenges of bucket wheel excavators is their enormous size and weight. Some of the largest machines, such as Bagger 288 or Bagger 293, weigh tens of thousands of tons and stretch hundreds of feet in length. This massive scale makes transport, assembly, and relocation difficult. Moving a BWE from one mine to another can take days or even weeks, requiring meticulous planning, specialized transport equipment, and temporary infrastructure modifications. These logistical challenges can limit flexibility in mining operations, particularly when projects span multiple sites or require rapid deployment. Another limitation is mobility constraints. Although some BWEs are mounted on tracks or crawlers, their movement is slow, often just a few meters per hour. This limited mobility means that repositioning the machine within a mine or adjusting to changing excavation phases can be time-consuming. Unlike smaller excavation equipment, BWEs cannot quickly adapt to shifting project requirements, making them best suited for large, continuous, and predictable mining areas. High capital investment is another challenge. Bucket wheel excavators are among the most expensive pieces of mining equipment. Purchasing, assembling, and commissioning a single machine can cost tens of millions of dollars. While they provide long-term cost efficiency, the initial investment is substantial and may not be feasible for smaller mining operations or projects with limited budgets. Financial planning and long-term forecasting are essential to justify such investments. Operational complexity presents another set of limitations. BWEs are intricate machines with thousands of moving parts, including the bucket wheel, boom, hydraulic systems, conveyor belts, and tracks. Coordinating all these components requires skilled operators, engineers, and maintenance teams. A single mechanical failure or misalignment can halt operations, resulting in costly downtime. Additionally, operating such complex machinery requires continuous training and adaptation to evolving technology, making workforce development a critical consideration. Environmental constraints also pose significant challenges. Surface mining operations with BWEs can cause land disturbance, soil erosion, and ecosystem disruption. Regulatory compliance is strict in the United States, requiring detailed environmental impact assessments, dust control measures, noise mitigation, and land reclamation plans. Any failure to adhere to these regulations can result in fines, legal action, or project delays. These environmental responsibilities add both complexity and cost to BWE operations. Another limitation is energy consumption. Bucket wheel excavators are highly energy-intensive machines. Continuous operation requires substantial electricity or diesel fuel, which can lead to high operational costs and carbon emissions. While advancements in energy-efficient designs and hybrid systems are mitigating this issue, energy consumption remains a significant consideration for both economic and environmental planning. Wear and tear is also a constant challenge. The abrasive materials these machines excavate, such as coal, lignite, clay, and rock, quickly wear down buckets, teeth, hydraulic components, and conveyor systems. Preventive maintenance and replacement of worn parts are essential to avoid unplanned downtime, but this requires careful planning, skilled labor, and access to spare parts. In remote mining locations, ensuring a steady supply of maintenance resources can be difficult. Weather and environmental conditions further affect BWE operations. Heavy rain, snow, or extreme temperatures can impact the movement of tracks, reduce traction, or affect hydraulic and electrical systems. Operators must continuously adjust machine settings, which adds operational complexity and may slow production during adverse conditions. Another limitation is initial site preparation. Because BWEs are massive, mining sites must be carefully prepared to support the weight and movement of these machines. This may involve grading, reinforcing the ground, or constructing temporary access roads and platforms. Such preparation increases upfront costs and requires detailed planning. Finally, economic and market constraints influence BWE utilization. While these machines are highly efficient for large-scale operations, smaller mines or projects with fluctuating demand may not benefit from such high-capacity equipment. If market conditions change or mineral prices drop, the investment in a bucket wheel excavator may not yield the expected return, making financial risk management an important consideration. Despite these challenges, engineering innovations, automation, predictive maintenance, and advanced planning continue to mitigate many of these limitations. Skilled operators, careful site selection, and adherence to environmental and safety standards allow BWEs to maintain their status as some of the most productive and efficient machines in the world. In summary, Chapter 9 has explored the challenges and limitations of bucket wheel excavators, including size and weight, mobility constraints, high capital investment, operational complexity, environmental and regulatory compliance, energy consumption, wear and tear, weather effects, site preparation, and economic considerations. Understanding these limitations helps mining companies plan effectively, maximize productivity, and ensure the safe and sustainable operation of these incredible machines. In the next chapter, we will focus on innovations and adaptations in design, exploring how engineers are addressing these challenges to make bucket wheel excavators even more efficient, versatile, and sustainable for future mining operations. Welcome to Chapter 10 of our series on bucket wheel excavators. In this chapter, we will explore the latest innovations and adaptations in the design of these massive machines. Engineering advancements are continually pushing the boundaries of what bucket wheel excavators can achieve, making them more efficient, versatile, and environmentally friendly. Understanding these design improvements is crucial for engineers, mining operators, and industrial planners, especially in the United States, where efficiency, safety, and sustainability are key priorities. One of the most significant innovations in BWE design is enhanced automation and control systems. Modern excavators are equipped with advanced sensors, software, and artificial intelligence that allow for semi-automatic or fully automated operation. These systems monitor key parameters such as vibration, load, hydraulic pressure, and structural stress, providing real-time feedback to operators or automatically adjusting operations to maintain efficiency and prevent damage. Automation reduces human error, improves safety, and ensures continuous high-volume excavation. Adaptive bucket wheel technology is another major advancement. Traditional bucket wheels had fixed sizes and shapes, but modern BWEs can feature modular or adjustable buckets designed to handle a variety of materials. Engineers can customize the bucket arrangement and cutting-edge profiles to optimize performance for soft soil, compacted earth, lignite, or even harder rock. This adaptability allows a single machine to be deployed across different mining environments, increasing its versatility and economic value. Energy efficiency and power management have seen significant improvements in recent BWE designs. Hybrid power systems combining electricity, diesel, and even renewable energy sources are increasingly common. Some excavators use regenerative braking or energy recovery systems, which capture energy during operations and reuse it elsewhere in the system. These innovations reduce overall fuel and electricity consumption, lower operational costs, and minimize the carbon footprint of the excavation process. Material handling integration is another key innovation. Modern BWEs often incorporate advanced conveyor systems, sorting mechanisms, and stockpile management tools directly into the machine. These systems reduce the need for secondary transportation, minimize material handling losses, and improve overall productivity. In some cases, BWEs are equipped with integrated screening and separation technology, allowing operators to sort excavated material immediately, which enhances efficiency and supports sustainable mining practices. Structural and material innovations have also transformed BWE design. Engineers are using lightweight but high-strength materials, such as advanced steel alloys and composite reinforcements, to reduce overall weight while maintaining durability. Wear-resistant coatings and replaceable modular components extend the lifespan of critical parts such as bucket teeth, conveyor belts, and hydraulic systems. These improvements reduce maintenance costs and minimize operational downtime. Environmental adaptations are increasingly integrated into modern BWEs. Dust suppression systems, noise reduction technologies, and water recycling mechanisms help minimize environmental impact. For instance, enclosed conveyor systems and high-pressure water sprays reduce dust emission, while insulated cabins and noise-dampening materials protect operators and nearby communities. These environmental adaptations are particularly important in the United States, where regulatory compliance and sustainable practices are highly valued. Remote operation and connectivity are transforming how BWEs are managed. Operators can now control machines from centralized command centers using high-speed data connections and real-time monitoring. This allows for precise coordination between multiple machines, efficient material transport, and remote troubleshooting. In challenging or hazardous mining environments, remote operation enhances safety and operational efficiency. Another important innovation is the use of digital twins and simulation technology. Engineers create virtual replicas of the excavator to model operations, predict maintenance needs, and optimize performance. By simulating different excavation scenarios, teams can plan operations more effectively, reduce risks, and enhance productivity. Digital twins also support training programs, allowing operators to practice and understand complex machine behavior in a virtual environment before actual deployment. Modular and scalable design is gaining prominence as well. Modern BWEs can be constructed in sections or modules, making assembly, transportation, and upgrades easier. This modular approach allows mining companies to scale their operations, retrofit machines with new technologies, and adapt to changing project requirements without investing in entirely new equipment. Finally, safety-focused innovations continue to evolve. Operator cabins are now ergonomically designed with advanced controls, vibration reduction, and enhanced visibility. Sensors alert operators to potential collisions, overloading, or structural stress, and automated shutdown procedures prevent accidents. These safety improvements not only protect personnel, but also reduce downtime caused by operational errors or hazardous conditions. In summary, Chapter 10 has explored the latest innovations and adaptations in the design of bucket wheel excavators. We've discussed automation, adaptive bucket technology, energy efficiency, material handling integration, structural improvements, environmental adaptations, remote operation, digital twins, modular design, and safety innovations. These advancements are shaping the next generation of BWEs, making them more efficient, versatile, and sustainable for large-scale mining operations, particularly in the United States. In the next chapter, we will focus on the comprehensive summary and future outlook for bucket wheel excavators, reflecting on all the topics we have covered so far and exploring the path forward for this remarkable engineering achievement. Welcome to Chapter 11, the final chapter of our series on bucket wheel excavators. In this chapter, we will summarize the key points we have explored throughout the series and look ahead to the future outlook of these remarkable machines. Bucket wheel excavators are not only marvels of engineering but also pivotal tools in the global mining industry, especially in the United States, where they support energy production, industrial growth, and technological innovation. Over the course of this series, we began by understanding the history and evolution of bucket wheel excavators. From early designs in Europe to the massive modern machines like Bagger 288 and Bagger 293, BWEs have evolved to handle ever larger volumes of material, operate continuously, and incorporate advanced technology. This historical perspective shows how engineering ingenuity has continuously pushed the limits of size, efficiency, and capability. We explore the mechanical components and operational principles of BWEs, highlighting how the bucket wheel, boom, conveyor systems, and tracks work together in perfect coordination. Understanding these components is essential to appreciate the complexity of operation and the precision engineering required to achieve high efficiency. Each part, from the rotating wheel to the hydraulic controls, plays a critical role in making these machines reliable and productive. The series also emphasized maintenance, safety, and operational challenges. We saw that operating a BWE requires meticulous planning, preventive maintenance, and skilled operators. Safety protocols are crucial because these machines are massive and potentially dangerous. Daily inspections, predictive maintenance, and operator training ensure that these machines continue to function efficiently while minimizing risk. We delved into the environmental impact and sustainability considerations. BWEs operate in large-scale surface mines, which can disturb landscapes, affect ecosystems, and generate dust and noise. However, modern practices such as dust suppression, water management, noise reduction, and land reclamation demonstrate how mining companies balance productivity with environmental responsibility. Sustainability has become a central focus in designing and operating these machines, particularly in the United States, where regulations and public expectations demand responsible mining. Our exploration of future advancements and technological innovations highlighted exciting developments such as automation, AI integration, sensor technology, energy efficiency improvements, remote operation, digital twins, and modular designs. These innovations are transforming how BWEs operate, making them safer, more efficient, and environmentally friendly. Adaptive designs, real-time monitoring, and predictive maintenance ensure that future machines will continue to push the boundaries of mining capability while reducing risks and environmental impact. Through global case studies, we examined iconic machines and mining operations around the world. Examples from Germany, India, North America, and specialized industrial applications illustrated the versatility, scale, and impact of BWEs. These case studies showed that, while designs and sizes may vary, the principles of efficiency, reliability, and innovation are universal. They also highlighted best practices that can be applied to new projects worldwide. We analyzed the economic and industrial significance of bucket wheel excavators. They are critical assets for productivity, cost efficiency, supply chain reliability, and regional economic development. Despite the high capital investment, their ability to move massive volumes of material efficiently and continuously provides an exceptional return on investment. BWEs also support job creation, workforce training, and industrial growth, ensuring that they remain indispensable in large-scale mining operations. We discussed the challenges and limitations of BWEs, including their size, mobility constraints, high operational complexity, energy consumption, environmental compliance, and market considerations. Understanding these limitations is crucial for mining companies to plan effectively, mitigate risks, and optimize operations. Engineers and operators continue to address these challenges through design innovations, automation, and strategic planning. Looking forward, the future outlook of bucket wheel excavators is promising. Machines will become increasingly autonomous, energy efficient, and adaptable to diverse mining environments. Advanced materials, modular construction, and integrated processing systems will enhance productivity and reduce operational costs. Environmental sustainability will remain a top priority, with technologies designed to minimize ecological disruption and maximize resource efficiency. The role of human operators will also evolve. While automation will handle routine and repetitive tasks, skilled professionals will remain essential for overseeing operations, interpreting data, and making critical decisions. The collaboration between humans and machines will define the next era of mining excellence, combining safety, efficiency, and innovation. In summary, bucket wheel excavators are more than just large machines. They are central to the future of mining and industrial operations. They embody the intersection of engineering, economics, technology, and environmental stewardship. From historical evolution to cutting-edge innovations, from global case studies to economic impact, BWEs represent the pinnacle of mining machinery. As we conclude this series, it is clear that bucket wheel excavators will continue to play a vital role in meeting the world's resource needs efficiently and sustainably. Their future is bright, driven by technological innovation, environmental responsibility, and the ongoing pursuit of operational excellence. For mining professionals, engineers, and enthusiasts, understanding these machines provides not only technical insight but also inspiration for what human ingenuity can achieve in industrial engineering. Thank you for joining us on this comprehensive journey through the world of bucket wheel excavators. We hope this series has provided a deep understanding, practical knowledge, and appreciation for these incredible machines and their impact on the mining industry and beyond. Welcome to Chapter 12 of our extended series on bucket wheel excavators. In this chapter, we will dive into the world of technological integration and smart mining, focusing on how modern digital technologies, artificial intelligence, and advanced data analytics are transforming the way these machines operate. Understanding these innovations is crucial for mining professionals, engineers, and industrial planners, especially in the United States, where mining operations are increasingly leveraging cutting-edge technology to maximize efficiency, safety, and sustainability. One of the most significant technological trends in modern BWEs is automation and autonomous operation. While traditional bucket wheel excavators require constant human oversight, new generation machines can operate semi-autonomously or fully autonomously. This is achieved through a combination of GPS systems, advanced sensors, and AI-driven algorithms that monitor excavation depth, wheel speed, conveyor operation, and material handling. Autonomous operation reduces human error, allows for continuous operation, and significantly increases productivity. Sensor technology plays a vital role in smart mining. Modern BWEs are equipped with sensors that track vibration, load distribution, structural integrity, and environmental conditions. These sensors provide real-time data to operators and central monitoring systems. For example, they can detect uneven wear on the bucket wheel, overheating in hydraulic systems, or excessive vibration in conveyor belts. Early detection of these issues prevents downtime, reduces maintenance costs, and improves overall safety. Integration with IoT, Internet of Things, allows BWEs to communicate with other machines and systems in the mining operation. IoT connectivity enables real-time coordination between multiple excavators, haul trucks, conveyor belts, and processing plants. This level of integration ensures that material flow is optimized, bottlenecks are minimized, and the overall mining process operates smoothly and efficiently. Predictive analytics and AI are becoming increasingly central to smart mining. By analyzing historical operational data, AI systems can predict maintenance needs, optimize bucket wheel speed, and adjust operational parameters to suit the type of material being excavated. Predictive maintenance prevents costly breakdowns and maximizes uptime, while AI-driven optimization ensures that energy use and operational efficiency are balanced for maximum productivity. Remote monitoring and control are also transforming BWE operations. Operators can oversee machines from centralized command centers, sometimes hundreds of miles away from the actual mine site. High-speed communication networks, cloud-based data storage, and real-time analytics allow operators to control multiple machines simultaneously, monitor performance, and make adjustments without being physically present. This not only improves safety but also allows for more efficient allocation of human resources. Digital twins are another revolutionary innovation. A digital twin is a virtual replica of the BWE that simulates its operations in real time. Engineers and operators can use digital twins to test different excavation strategies, forecast maintenance needs, and train new personnel without risking damage to the actual machine. This technology enables precise planning, reduces operational risk, and enhances training effectiveness. Energy management systems are also integrated into smart BWEs. Advanced power monitoring allows operators to track energy consumption, identify inefficiencies, and implement energy-saving strategies. Some systems incorporate renewable energy sources, hybrid power systems, or energy recovery mechanisms, further reducing the environmental footprint and operational costs of large-scale mining operations. Safety technology is deeply integrated into modern smart mining operations. BWEs now feature collision detection, emergency shutdown systems, and advanced alarms for structural stress or component failure. AI-assisted safety systems can even predict hazardous scenarios, allowing operators to take preventive action before accidents occur. These safety innovations are especially important in the United States, where regulatory standards for industrial safety are stringent and closely monitored. The integration of augmented reality, AR, and virtual reality, VR, is also gaining traction. Engineers and operators can use AR to visualize the internal systems of the BWE, identify maintenance needs, and simulate different operational scenarios. VR can be used for immersive training programs, allowing operators to experience complex machine behavior in a virtual environment before working on the real machine. Finally, big data analytics is revolutionizing the strategic planning of mining operations. By aggregating data from multiple BWEs, haul trucks, processing plants, and environmental sensors, mining companies can gain insights into overall productivity, resource utilization, and operational efficiency. These insights inform decision-making, improve resource allocation, and support long-term planning for sustainable mining operations. In summary, Chapter 12 has explored technological integration and smart mining with bucket wheel excavators. We have discussed automation, sensors, IoT connectivity, predictive analytics, remote monitoring, digital twins, energy management, safety technology, AR and VR, and big data analytics. These innovations are transforming BWEs into smart, highly efficient, and environmentally responsible machines, shaping the future of mining operations not only in the United States but across the globe. As we continue to advance in the field of mining technology, the integration of these innovations ensures that bucket wheel excavators will remain at the forefront of industrial efficiency, safety, and sustainability, paving the way for smarter, more productive, and more responsible mining practices. Welcome to Chapter 13 of our extended series on bucket wheel excavators. In this chapter, we will explore advanced materials and engineering innovations that are shaping the future of these massive machines. Material science and engineering ingenuity play a critical role in improving the performance, durability, and efficiency of BWEs. These innovations are particularly relevant in the United States, where mining operations demand both high productivity and adherence to strict safety and environmental standards. One of the most critical areas of innovation is the use of high-strength steel and alloys. Traditional steel, while durable, is heavy and subject to wear and fatigue under the immense loads handled by BWEs. Modern machines incorporate advanced steel alloys that offer superior strength-to-weight ratios. These alloys allow engineers to design larger, more capable machines without excessively increasing weight, which improves mobility and reduces stress on tracks, hydraulic systems, and foundations. Wear-resistant materials have also revolutionized BWE durability. Bucket teeth, cutting edges, and conveyor components are exposed to abrasive materials such as coal, lignite, clay, and rock. Engineers now use hardened steel, tungsten carbide coatings, and other wear-resistant materials to extend the lifespan of these components. This reduces maintenance downtime, lowers operational costs, and ensures continuous, efficient excavation even under harsh conditions. Another innovation is the use of composite materials in non-structural components. Lightweight composites are increasingly being used for operator cabins, conveyor housings, and protective shields. These materials reduce the overall weight of the machine, improve fuel or energy efficiency, and enhance operator safety by absorbing vibrations and impacts. Advanced composites also resist corrosion, making them ideal for challenging environmental conditions. Hydraulic system innovations have significantly improved BWE performance. Engineers are now designing variable flow and variable pressure hydraulic systems that optimize power delivery to the bucket wheel, boom, and conveyor systems. These smart hydraulic systems reduce energy consumption, minimize wear on critical components, and allow for smoother, more precise operation. Coupled with real-time monitoring, these systems enhance both efficiency and safety. Advanced conveyor technologies are another key innovation. Modern BWEs incorporate high-capacity, modular conveyor belts made of reinforced materials that can withstand heavy loads and abrasive conditions. Innovations such as energy-efficient motors, intelligent belt tensioning systems, and dust-proof enclosures increase reliability, reduce maintenance requirements, and support continuous operation. Some conveyors also feature integrated sorting or screening systems, allowing for more efficient material handling. Vibration and structural damping innovations enhance machine stability and longevity. Engineers are using vibration dampening materials and designs to reduce structural stress on critical components. These innovations not only extend the lifespan of the machine, but also improve safety for operators by minimizing vibrations transmitted to cabins and control systems. Modular engineering designs are increasingly applied to BWEs. Modular components allow for easier assembly, maintenance, and upgrades. Sections of the bucket wheel, boom, or conveyor can be replaced individually without dismantling the entire machine. This flexibility reduces downtime, allows for quicker adaptation to different mining environments, and supports cost-effective upgrades as new technologies become available. Corrosion-resistant coatings and treatments are critical for machines operating in humid, wet, or chemically reactive environments. Advanced coatings protect structural steel, hydraulic systems, and conveyor components from rust, chemical exposure, and environmental degradation. These materials ensure longevity, reduce maintenance needs, and preserve operational efficiency over years of continuous use. Sensor-embedded materials are a cutting-edge innovation in BWE engineering. Some components now include embedded sensors that monitor temperature, stress, vibration, and wear in real time. These smart materials provide data to predictive maintenance systems, allowing engineers to detect issues before they become critical. This integration of materials and technology exemplifies the next level of intelligent machine design. Finally, ergonomic and safety-focused material innovations improve the operator experience. Modern cabins use advanced cushioning materials, noise insulation, and anti-vibration mounts. Transparent, impact-resistant panels and enhanced climate control improve visibility and comfort, ensuring operators can maintain focus and efficiency over long shifts. In summary, Chapter 13 has explored advanced materials and engineering innovations in bucket wheel excavators. We have discussed high-strength steel and alloys, wear-resistant materials, composites, hydraulic innovations, advanced conveyor technologies, vibration damping, modular designs, corrosion resistance, sensor-embedded materials, and operator-focused improvements. These innovations collectively enhance the durability, efficiency, safety, and sustainability of BWEs, ensuring that they remain the backbone of modern, large-scale mining operations. The integration of advanced materials with innovative engineering solutions positions bucket wheel excavators at the forefront of industrial machinery, ready to meet the growing demands of energy production, mineral extraction, and sustainable industrial development, particularly in the United States. In the next chapter, we will focus on environmental sustainability and green mining practices with bucket wheel excavators, exploring how technological, operational, and material innovations contribute to environmentally responsible mining. Welcome to Chapter 14 of our extended series on bucket wheel excavators. In this chapter, we will explore environmental sustainability and green mining practices, highlighting how modern bucket wheel excavators are being designed and operated to minimize ecological impact while maximizing productivity. This topic is particularly relevant in the United States, where mining regulations are strict and public expectations for environmental responsibility are high. One of the most important aspects of green mining with BWEs is dust and air quality management. Large-scale excavation generates significant dust, which can affect both workers and nearby communities. Modern BWEs are equipped with dust suppression systems, including high-pressure water sprays, enclosed conveyor belts, and air filtration technologies. These systems reduce airborne particles, ensuring compliance with environmental standards and improving the health and safety of personnel and surrounding areas. Noise reduction is another critical component of sustainable operations. BWEs are inherently loud due to their massive motors, conveyors, and moving parts. Engineers have developed noise-dampening solutions, such as insulated cabins, vibration-dampening materials, and sound barriers around key components. These innovations help reduce the impact of mining noise on local communities and wildlife. Energy efficiency and emission reduction are also central to green mining practices. Modern BWEs utilize hybrid power systems, energy recovery technologies, and high-efficiency motors to reduce fuel consumption and greenhouse gas emissions. For instance, some machines use regenerative braking systems that capture energy during operation and return it to the machine's electrical systems. By improving energy efficiency, mining companies can reduce costs and environmental impact simultaneously. Water management and recycling are increasingly integrated into BWE operations. Excavation often requires significant water usage for dust suppression, cooling, and material processing. Sustainable practices involve capturing and recycling water within the mining site, using closed-loop systems to minimize freshwater consumption and prevent contamination of local water sources. These practices are essential for compliance with U.S. environmental regulations and for maintaining community trust. Land reclamation and restoration are vital long-term sustainability practices. Once mining areas are excavated, companies use strategic planning to restore the land to a safe, usable, or even ecologically beneficial state. This may involve contouring the landscape, planting vegetation, creating artificial lakes, or establishing wildlife habitats. Modern BWEs, with their precision and high-volume excavation capabilities, allow for more controlled and efficient land management, making reclamation projects easier to implement. Integration with renewable energy sources is another innovation in sustainable mining. Some BWEs and mining operations incorporate solar panels, wind energy, or other renewable sources to power auxiliary systems and reduce dependency on fossil fuels. This reduces the carbon footprint of mining operations and contributes to broader environmental goals. Intelligent monitoring systems are increasingly used to track environmental impact in real time. Sensors monitor dust levels, noise, energy consumption, water usage, and emissions. These data are used to optimize operations, ensuring that productivity is balanced with environmental responsibility. In the United States, such systems help companies meet regulatory standards and provide transparency for community stakeholders. Collaborative ecosystem management is also becoming standard practice. Mining companies work with environmental agencies, local communities, and researchers to develop sustainable practices that minimize ecological disruption. This includes protecting wildlife corridors, preserving soil quality, and maintaining water tables. BWEs, when operated thoughtfully, allow for efficient extraction while supporting these broader sustainability goals. Waste management and material recycling are integral to green mining. Modern BWEs, often equipped with sorting and screening capabilities, can separate usable materials from waste directly at the excavation site. This reduces the need for additional processing and minimizes environmental impact. Reusing excavated materials for land restoration, construction, or industrial applications further enhances sustainability. Finally, continuous innovation in green technology ensures that BWEs will become increasingly environmentally responsible. Engineers are exploring lightweight, corrosion-resistant materials, low-noise components, energy-efficient motors, and automated systems to optimize resource use and minimize ecological impact. These innovations not only support sustainable mining practices, but also enhance operational efficiency and cost-effectiveness. In summary, Chapter 14 has explored environmental sustainability and green mining practices with bucket wheel excavators. We have discussed dust and air quality management, noise reduction, energy efficiency, water recycling, land reclamation, renewable energy integration, intelligent monitoring, ecosystem collaboration, waste management, and ongoing innovations in green technology. These practices ensure that modern BWEs can meet the growing demands of mining while minimizing ecological disruption and promoting sustainable industrial practices. By combining technological innovation with environmental stewardship, bucket wheel excavators exemplify how large-scale mining can be productive, safe, and environmentally responsible. As we move forward, sustainable practices will continue to shape the design, operation, and impact of these remarkable machines. Welcome to Chapter 15, the final chapter of our extended series on bucket wheel excavators. In this chapter, we will explore the future trends and innovations shaping the next generation of these massive machines. As mining demands grow and technology evolves, bucket wheel excavators are set to become smarter, more efficient, and environmentally responsible than ever before. Understanding these future trends is essential for engineers, mining professionals, and industrial planners, particularly in the United States, where innovation, sustainability, and efficiency are key drivers of industrial success. One major trend is increased automation and artificial intelligence. Next-generation BWEs will leverage AI to optimize excavation processes in real time, adjusting bucket rotation speed, conveyor operation, and energy use based on the type and consistency of the material being excavated. Predictive AI systems will also monitor wear and tear, anticipate maintenance needs, and optimize operational schedules. This will reduce downtime, increase productivity, and ensure the machine operates at peak efficiency continuously. Integration with smart mining ecosystems is another critical development. BWEs of the future will not operate in isolation. They will be part of fully connected, data-driven mining networks. Through the Internet of Things, IoT, cloud computing, and advanced analytics, multiple machines, haul trucks, and processing plants will communicate in real time, optimizing material flow, energy consumption, and operational coordination. This connectivity will allow mining companies to achieve unprecedented levels of efficiency and control. Energy efficiency and sustainability innovations will be central to the next generation of BWEs. Hybrid power systems combining electricity, renewable energy sources, and energy recovery technologies will reduce reliance on fossil fuels and lower greenhouse gas emissions. Regenerative braking, smart power distribution, and lightweight energy-efficient components will contribute to greener operations. These energy-focused innovations are particularly important in the United States, where environmental regulations and corporate sustainability initiatives are stringent. Advanced materials and structural innovations will make future BWEs stronger, lighter, and more durable. High-strength alloys, composites, and wear-resistant coatings will allow machines to handle heavier loads and harsher conditions without excessive weight or frequent maintenance. Modular designs will make assembly, upgrades, and repairs faster and more cost-effective, while reducing operational downtime. These material innovations will also extend the lifespan of machines, making long-term investment in BWEs even more viable. Enhanced safety systems will be a major focus in future designs. AI-assisted monitoring, automated shutdown systems, collision detection, and operator support technologies will ensure that both machines and personnel are protected. Remote operation and virtual training using augmented reality, AR, and virtual reality, VR, will further reduce human risk while enhancing operational precision. Safety innovations will also comply with evolving industry standards and regulatory requirements. Data-driven decision-making and predictive analytics will revolutionize operational planning. Future BWEs will continuously collect data on machine performance, environmental conditions, and material properties. This data will be analyzed using machine learning to provide actionable insights, optimize extraction strategies, and anticipate challenges before they occur. Mining companies will be able to make informed, real-time decisions that maximize output while minimizing costs and environmental impact. Environmental innovations and green mining practices will continue to advance. Next-generation BWEs will integrate dust suppression, noise reduction, water recycling, and land reclamation features as standard. Machines will be designed to minimize ecological impact while maintaining high productivity, supporting sustainable mining practices and regulatory compliance. Renewable energy integration, emission reduction, and efficient resource utilization will be central to the design philosophy of future excavators. Global positioning and precision mining technologies will allow BWEs to operate with unprecedented accuracy. Advanced GPS, laser scanning, and geospatial mapping systems will guide excavation with centimeter-level precision. This ensures minimal waste, reduces environmental disruption, and maximizes resource extraction efficiency. Precision mining will also enhance safety by preventing unintended over-excavation or instability in mining sites. Human-machine collaboration will evolve. While automation will handle routine tasks, skilled professionals will focus on decision-making, strategy, and oversight. AR, VR, and haptic feedback systems will allow operators to interact with machines virtually, improving training, precision, and responsiveness. This collaborative approach combines the best of human expertise